Good evening everyone, good evening. I welcome you all again to JEE Enthuse. I hope you all are doing great, having a good time. So people, just let me know in the chats first of all if I'm perfectly audible and visible to everyone, right? Hello Afreen, hi Dakshin, hi Ishpreet. Hello Nati Tamil, hello Sana, hi Nandini, hello Ashwarya. Welcome back everyone, welcome back. Just let me know first of all in the chats if I'm perfectly audible and visible to everyone. Let me know fast people, let me know fast. Just give me a second, we'll be starting, yeah? Alright, so people, as you all must be knowing, tonight it's going to be a sprint session from the chapter Chemical Equilibrium, right? And in the tonight's session, I have come up with around 20 to 25 questions. By solving these, your entire chemical equilibrium chapter is going to get revised, right? So before starting the session, the ones who have just joined in, the ones who are new to the channel, let me quickly introduce myself. Well people, my name is Wassim and I'm your chemistry master teacher right here on this JEE Enthuse channel, right? Well, the ones who have not liked the video yet, please do like the video, share the video with your friends, do subscribe to the channel and do not forget to hit the bell icon so that you get the notification of every single session which we take live on this JEE Enthuse channel, right? So do like the video, share the video with your friends and do subscribe to the channel as well. I'm better than before guys, I'm better than before. Perfect. Just let me know fast in the chats if all of you are super duper excited about the tonight's session as well people. Let me know fast in the chats if all of you are super duper excited about the tonight's session. Yes, let me know fast in the chats. Perfecto. Wonderful. Alright guys, so let's get going then. Let's get started with the first question from the chapter Chemical Equilibrium, which is going to be on your screen in 3, 2, 1 and now. This is a first question with which I'm starting. Very simple and basic question, right? Let's see exactly what the question says and let's see exactly how this sort of equation is to be solved. Well, before solving this question, let me tell you a few important things, few basic and important things. Let's say I have got a general reaction in which A and B, right, are in equilibrium with C and D. Let's say this is one general reaction which I have. A plus B in equilibrium with C plus D, right? Let's assume the equilibrium constant for this reaction I'm representing with K. Let's assume this K is the equilibrium constant for this particular reaction. Now people, do remember, whenever we multiply any reaction by certain number, that number goes to the power of equilibrium constant. For example, if I multiply this reaction by some number n, it becomes n times A plus n times B in equilibrium with n times C plus n times D. So basically, this particular reaction which was at equilibrium, I have multiplied this reaction by the number n. That number now goes to the power of equilibrium constant. So the new equilibrium constant for this reaction becomes K raised power n, right? Perfect. Now, one more thing. If we reverse this reaction, the reaction becomes C plus D in equilibrium with A plus B. And do remember, whenever we reverse a reaction, equilibrium constant is inversed. So the new equilibrium constant for this reaction is going to be 1 divided by K. Perfect. At the same time, whenever we add two reactions, their equilibrium constants are to be multiplied. Right? For example, I've got one reaction as A in equilibrium with B, whose equilibrium constant is K1. I've got one more reaction in which C is in equilibrium with D, whose equilibrium constant is K2. If I add these two reactions, I'll get a new reaction, which is going to be A plus C in equilibrium with B plus D. What is going to be the new equilibrium constant for this reaction? It's going to be simply K1 multiplied by K2. Perfect. So I'm sure you guys would have remembered all these things which I told you just now, right? Perfect. Now let's try to solve the question which is on your screen. The equilibrium constant for the reaction, we are given with a reaction in which N2 reacts with O2 and in equilibrium with 2 times NO. Correct? The equilibrium constant for the reaction is given to us as right? Equilibrium constant for the reaction is given to us as 4 into 10 raised power minus 4. The value of equilibrium constant for this particular reaction, I need to calculate the equilibrium constant for this particular reaction. Now people, in order to calculate equilibrium constant for this particular reaction, I need to make this reaction first. I need to make this reaction first out of the given reaction. So how do I make this particular reaction out of the given reaction? What I'll be doing first of all, I'll be just reversing this reaction. If I reverse this reaction, it becomes 2 times NO in equilibrium with N2 plus O2. And as I told you, when we reverse the reaction, equilibrium constant is inversed. So new equilibrium constant for this reaction is going to be 1 divided by 4 into 10 raised to the power minus 4, right? Now what I'll be doing afterwards, I will be multiplying this reaction with 1 by 2. When I multiply this reaction with 1 by 2, it becomes NO in equilibrium with 1 by 2 times N2 plus 1 by 2 times O2. Since I've multiplied this reaction by 1 by 2, okay, that 1 by 2 goes to the power of equilibrium constant. So the new equilibrium constant will simply become raised to the power 1 by 2. Raised to the power 1 by 2, right? As simple as that. Since I multiplied this reaction by 1 by 2, that 1 by 2 goes to the power of equilibrium constant. So did I make the reaction whose equilibrium constant was to be calculated? Yes, I made the reaction. So what is its new equilibrium constant now? It's this 10 raised power 4 will go up. It's going to be 10 raised power 4 divided by 4 raised to the power 1 by 2. The value comes out to be 100 divided by 2. That means 50. So the new equilibrium constant for the reaction exactly is going to be 5050, which is option D. Just let me know in the chats if it is clear to everyone, right? Just let me know fast. Yes, Ankit, that is absolutely important. Have a look on that as well. Perfect. A very similar basic question it was. So let's directly move on to one more question there. This is one more question on the screen. Let's try to figure out how to tackle to this sort of equation. It's a very simple one again, right? A bit conceptual. Let's see exactly how to solve this question. See guys, as per this question, I'm given the reaction in which NH4HS, which is in solid form, it's in equilibrium with what? It's in equilibrium with NH3 gas. And with this NH3 gas, you're writing this H2S gas as well, right? You're writing H2S gas as well. This is the reaction that's given to me. If the pressure at equilibrium is 100 atm, so pressure of the system, right? Since this reaction will be taking place definitely in some container, when equilibrium will be established in this reaction, at that point of time, the pressure of the system at equilibrium is given to us as 100 atm. This is the total pressure of the system at equilibrium. Then, what will be the equilibrium constant Kp? First of all, people, this is in solid form. This reaction is first of all going to take place in a container, right? It's going to take place in a closed container, right? Since this one is in solid form, it has got no contribution towards the total pressure of the system at equilibrium. So I must say only this substance, which is in gaseous form, and this substance will contribute towards the total pressure at equilibrium, which is 100, right? Now people, the stoichiometric coefficients right here are 1 and 1. So I must say both these substances will contribute equally towards the total pressure of the system at equilibrium. Let's assume the contribution of NH3 towards the total pressure at equilibrium is P. That means contribution of this H2S towards the total pressure at equilibrium is again going to be P. So basically, this P is the partial pressure of NH3 at equilibrium. This P is the partial pressure of H2S at equilibrium. Or you can say this P is the contribution of NH3 towards the total pressure at equilibrium. This P is again the contribution towards the total pressure by H2S at equilibrium, right? If I use simply the Dalton's law of partial pressure, can I say at equilibrium the total pressure will be the sum of partial pressures of these two, which is P plus P, comes out to be 2P. Total pressure of the system at equilibrium is given to be as 100, so you can calculate P from here, which will come out to be 50 atm, right? You calculate exactly the value of P. Why did I calculate the value of P? Because I need to calculate the value of Kp, right? Do you remember how do we write the expression for Kp? Kp is nothing, it is just the partial pressure of NH3 at equilibrium raised to power stoichiometric coefficient 1 multiplied by partial pressure of H2S at equilibrium raised by its stoichiometric coefficient, that's 1. So the value simply will come out to be 50 multiplied by 50, and the value is finally going to be 2500 atm square, right? This is the value of Kp, which is going to be the final answer of the question, right? So is there any option like that? Yes, option A is the one which is going to be correct answer out of all, right, people? Ram, I'm better than before. Perfect. Perfect, guys. So let's move on then to one more question. I'm sure this sort of a question is clear to everyone. Yeah? Okay, moving on to one more. This is one more question. The equilibrium constant for a reaction A plus B in equilibrium with C plus D is 10 raised per minus 2 at 298 Kelvin and is 2 at 273 Kelvin. The chemical process resulting in the formation of C and D will be. Okay. See guys, what is the concept involved in this question? Let me make you understand the concept first of all. Then we'll talk about few important things. Let's say I've got the reaction as A plus B gives C plus D. Let's say it's a reaction. It's a general chemical reaction. Okay. Let's assume the equilibrium constant of this particular reaction is equal to K1 when the temperature of the reaction is kept T1. At temperature T1, the equilibrium constant of this reaction, for example, is K1. Perfect. Now, if I change the temperature from T1 to T2, let's assume the equilibrium constant of the reaction changes from K1 to K2. Perfect. Now, guys, I'm sure you would have studied chemical kinetics, right? In chemical kinetics, you would have studied one relation which used to be log of K2 divided by K1 is equal to delta H divided by 2.303 R multiplied by 1 upon T1 minus 1 upon T2. Or I can write T2 minus T1 divided by T1 T2. Let me write it that manner, right? It's going to be T2 minus T1 divided by T1 T2. Perfect. Let me assume the forward reaction over here is endothermic. Let's say this is the endothermic reaction. The forward reaction over here in which the product C and D is getting formed, let's assume that is endothermic. For endothermic reactions, you all must be knowing delta H value is positive. Delta H value is positive. That's something which every one of us would be knowing. I'm assuming T2 is greater than T1. If T2 is greater than T1, what does that mean? That means I'm increasing the temperature of the system, right? I'm increasing the temperature of the system. If I increase the temperature of the system for this particular endothermic reaction, if the temperature is increased, that means T2 will be greater than T1. If T2 is greater than T1, the difference between these two will come out to be positive. Positive and this positive makes it positive. So log of K2 divided by K1 value is positive, right? Log of K2 divided by K1 value is positive, which is only possible if K2 divided by K1 will be greater than 1, which simply tells you K2 is greater than K1, right? So what does that mean? That means for a particular endothermic reaction, on increasing the temperature, equilibrium constant increases. On increasing the temperature, equilibrium constant increases for an endothermic reaction, right? This is the first conclusion which I would want all of you to remember. For an endothermic reaction, on increasing the temperature, the equilibrium constant increases, right? But look at this question carefully. When the temperature of the system was kept 298 Kelvin, at that point of time, equilibrium constant was 10 raised per minus 2. When the temperature is changed from 298 to 273, that means I'm decreasing the temperature. On decreasing the temperature, what is happening to the new equilibrium constant? The new equilibrium constant now is 2. So basically, on decreasing the temperature, equilibrium constant increases. On decreasing the temperature, equilibrium constant is increasing. So is it going to be the endothermic reaction? No, because endothermic reactions ke liye, on increasing the temperature, equilibrium constant increases, right? Similarly, on decreasing the temperature, equilibrium constant decreases. So it is definitely going to be the exothermic reaction which is going to be following in this manner, right? I'm sure this is clear to everyone, right, people? Perfect. Inspire today. Surely I'll do that. Surely. Okay. Let's move on, people, to one more question. This is one more question. Let's try to solve this one as well. Again, a very simple and conceptual question, right? For a reaction A plus B in equilibrium with 2C, 2 moles of A, 1 mole of B and 1 mole of C are placed in a 10-liter vessel and allowed to reach equilibrium. If final concentration of C is 0.2 molar, then calculate the value of Kc. Perfect? Right? Let's see exactly how this sort of equation is to be solved. The reaction that's given to you as per the equation, the reaction is simple: A gas plus B gas in equilibrium with 2 times C gas. This is the reaction which I have, right? First thing, at time t is equal to 0, initially, how many moles of A am I given with? I'm given with 2 moles of this. I'm given with 1 mole of this, and at the same time, I'm given with 1 mole of C as well, okay? Now, let's assume at equilibrium, out of 2 moles of A, some X moles of A have reacted. If X moles of A has reacted, what just happened? What just happened? There is some error, I guess. Just a second, guys. Let me write the reaction again. The reaction is A plus B in equilibrium with 2 times C, and initially at time t is equal to 0, some 2 moles of A were given to me. In the similar way, I'm given with 1 mole of B, and at the same time at time t is equal to 0, we have got 1 mole of C as well. Perfect. Now when equilibrium will be established in the reaction, I'll be assuming out of 2 moles of A, some X moles have reacted. So I'll be left with 2 minus X moles of A at equilibrium. Similarly, 1 mole reacts with 1 mole, so X moles are going to react with X moles, right? So I'll be left with 1 minus X moles of B at equilibrium. And at the same time, already I had some 1 mole of C in the container. Now due to the reaction, some new moles of C would have got formed. 1 mole gives 2 moles. From X moles, you are going to get 2 X moles. So I got the moles of each reactant and product at equilibrium, right? Since I got the moles of each reactant and product at equilibrium, is the volume of the container in which the reaction takes place given to us? Yes, 10 liters. So they would divide this term by 10, divide this term by 10, divide this term by 10. I got the concentration of each reactant and product at equilibrium, right? Well, people, as per the equation, the system is allowed to reach equilibrium if the final concentration of C is 0.2 molar. So final concentration of C, what does that mean? That means concentration of C at equilibrium is given to me as per the equation, which is 0.2. Well, as per this equation is concerned, this is basically giving you the final concentration of C at equilibrium, which is 1 plus 2x divided by 10. This value is 0.2, that means 2 divided by 10, right? So from here, x value, you'll get it as 1 by 2, that means 0.5. You got the value of x exactly. Now I would want you guys to put the value of x in all these expressions. So it's going to be 2 minus 0.5, 1.5. 1.5 divided by 10 means 0.15, right? Similarly, 1 minus 0.5 will be 0.5, right? 0.5 divided by 10 is 0.05, right? This value, 1 plus 2x divided by 10. 1 plus 2x divided by 10 is equal to 2 by 10. That means 0.2. Well, I got the concentration of each reactant and product at equilibrium, right? If you got the concentration of each reactant and product at equilibrium, right, you can easily write the expression for Kc. Isn't it going to be concentration of C at equilibrium raised to the power of stoichiometric coefficient 2 divided by concentration of A at equilibrium raised to the power of stoichiometric coefficient 1 multiplied by concentration of B at equilibrium raised to the power of stoichiometric coefficient 1, right? Now you just need to put all these values into the given expression. Concentration of C at equilibrium is nothing, it is 0.2 raised to the power 2 divided by concentration of A at equilibrium is 0.15 multiplied by concentration of B at equilibrium again is 0.05. Now just you need to solve this part and get the value of Kc, which I was supposed to calculate, right? And the final answer, as far as I remember, will come out to be 16 divided by 3. Just let me know in the charts if it is clear to everyone. Yes? Let me know fast in the charts, people, if it is clear to every single guy. Perfect. So let's jump into one more question. Let's see what another question says. Okay, we are given the reaction. If the initial pressure of AB3 is 900 torr and the total pressure at equilibrium is 1000 torr, calculate Kp. A very simple question this again. There is one simple concept involved, that is Dalton's law of partial pressure. Let's try to solve the question with the help of Dalton's law of partial pressure. Let's see exactly what the question says. The question is simple. AB3 gas in equilibrium with AB2 gas plus 1 by 2, it's going to be B2 gas. This is the reaction which I'm having right now. This is the reaction which I'm having right now, yeah? Now understand. If the initial pressure of AB3 is 900 torr, right? And the total pressure at equilibrium is 1000 torr. So at time t is equal to 0, the initial pressure due to AB3 is 900 torr. So this is going to be 0, this is going to be 0, right? Now at equilibrium, I'm going to treat these pressures in the similar way as I used to treat the moles. At equilibrium, it's going to be 900 minus x. Now the way 1 mole used to give 1 mole, so from x you get x over here. 1 mole used to give 1 by 2 moles. Similarly from x, I'll be getting x by 2 over here. But people, is this 996 moles ki pressure? This is the pressure, right, at equilibrium. This is the pressure of AB3 at equilibrium. This X, it is basically the pressure of AB2 at equilibrium. This is the pressure of B2 at equilibrium, right? Yes. Basically, this reaction is taking place into the container. And when equilibrium was established in the reaction, the pressure due to AB3 was this much, due to AB2 was this much, due to B2 was this much. Well, the total pressure of the system at equilibrium is 1000 torr. Well, this is in gaseous phase, this is in gaseous phase, this is in gaseous phase. So all these three species at equilibrium will be definitely contributing towards the total pressure of the system at equilibrium. I must say, total pressure of the system at equilibrium is going to be equal to 900 minus 6 plus this X plus this X by 2, right? So this got cancelled. Total pressure of the system at equilibrium is given to me as 1000. So 1000 is equal to 900 plus X divided by 2. From this equation, you get the value of X as 200 torr. Right? From this equation, you get the value of X as 200 torr. Since you got the value of X exactly, what I was supposed to calculate? I was supposed to calculate the value of Kp. Since you got the X, put the value of X in all these expressions over here. It's going to be 900 minus 200, that means 700, right? So the contribution of AB3 at equilibrium towards the total pressure is going to be 700 torr. This is going to be simply 200 torr. And this one will be X by 2. X by 2 means 200 by 2. That means 100 torr. Correct? Correct, people? So you got basically the contribution of each species towards the total pressure at equilibrium. What was I supposed to calculate? I was supposed to calculate the Kp, I believe, right? So you guys know how to write the expression for Kp. It's simple. It's going to be partial pressure of AB2, which is 200 torr, raised by its stoichiometric coefficient 1, multiplied by partial pressure of B2 at equilibrium, which is 100, raised to the power its stoichiometric coefficient, that's 1 by 2, divided by partial pressure of AB3 at equilibrium, which is 700, raised by its stoichiometric coefficient, that's 1. And when you solve it, what is the final value you'll be getting? What is the final value you'll be getting, people? Well, you guys know now how to solve this, right? This 0000 cancel. 100 raised power 1 by 2 is 10. 2 multiplied by 10 is 20. So 20 divided by 7 is going to be the final answer. So it's going to be 2 point something. Is there any option as 2 point something? Yes, it's option B, which is coming out with the final answer of the question, right? Perfect. Is it clear to everyone? All right, guys. Moving on to one more question then. Let's see what the next question says. See, a very simple question. This is a very simple question. Just you need to see the relation between Kp and Kc, right? See, guys, there is one thing which you need to know right here. What is that going to be? The reaction that's given to me, I will be calculating this delta Ng first of all, and delta Ng for this reaction is going to be equal to number of moles of gaseous products minus number of moles of gaseous reactants. The value comes out to be minus 2, right? Delta Ng for the particular reaction is given to me as minus 2. Now I need to see, is Kp greater than Kc or Kc greater than Kp? What is the actual ratio, right? And the reaction is carried out at 10 Kelvin. Reaction is carried out at 10 Kelvin, right? Okay. Now you guys know Kp is equal, for a gaseous phase reaction carried out at constant temperature, Kp is equal to Kc RT raised to the power delta Ng, right? This is valid for a gaseous phase reaction carried out at constant temperature. Perfect. What is the value of R? R value, you guys know, it's 1 by 12. atm liter per Kelvin per mole, right? Now guys, understand one important thing. If R value is 1 by 12, temperature of the reaction is given to us as 10, right? Temperature of the reaction is given to us as 10 Kelvin, right? So the product of these two, is it going to be greater than 1 or less than 1? The product of these two is going to be less than 1. Perfect. So I'll be writing Kp is equal to Kc. Instead of RT, you are basically getting some term which is less than 1. Let's keep it as 0.8 for example. Raised by delta Ng. Delta Ng is what? Delta Ng is minus 2, right? Now check it out. Check it out people exactly. Is Kp going to be greater than Kc or Kc going to be greater than Kp? Now you can take it into the denominator. You can write it as Kp multiplied by 0.8 raised to the power 2 is equal to Kc. So from this, you'll exactly get the idea which one is going to be more, Kp or Kc. It's absolutely going to be Kp, which will be more than that of Kc. Because Rt value, product of R and T, was coming out to be less than 1, right? Perfect. Right, people? So this value, Rt value, was coming out to be less than 1. So finally, you can see Kp will be greater than Kc. Yeah? Perfect. Okay. Let's see exactly one more question. This is one more simple question. on the basis of vapor density measurement. The vapor density of N2O4 and NO2 mixture at a certain temperature at equilibrium is 30. The vapor density of the equilibrium mixture, which I represent with small d, is given to me as 30. Calculate the percentage dissociation of N2O4 at the same temperature, right? First thing, I hope you remember, in case of dissociation by vapor density measurement, alpha is equal to capital D minus small d divided by small d multiplied by n minus 1. This relation is valid in case of your dissociation, right? And this is a particular case of dissociation, as you can see over here, right? Now understand few things, people. What is capital D? Capital D is the theoretical vapor density, right? Or you can say capital D is basically the vapor density of the reactant at time t is equal to 0. Vapor density of reactant at time t is equal to 0, which is going to be equal to molar mass of reactant, which is 92 grams per mole, divided by 2. The value comes out to be 46. So capital D value you got, small d value you got. What is the value of N? See, from one particle you are getting two particles. From one particle you are getting two particles. The number of particles which we get from one particle, right, that decides the value of N. N value is 2 in this case. So alpha value is equal to capital D, which is 46 minus small d, which is 30, small d, which is 30, n minus 1, that means 2 minus 1 comes out to be 1. So it comes out to be simply 16 divided by 30. Just solve it. That's going to be giving you the degree of dissociation. And if you got the degree of dissociation, you can calculate the percentage dissociation as well. And percentage dissociation is simply going to be alpha multiplied by 100. So it's 16 divided by 30 multiplied by 100. Right, people? Perfect. Now, get it sorted and get the value exactly of percentage dissociation, and the final answer will come out to be 53%, right? I'm sure it is super clear to everyone, right? Let me know fast in the chat if it's clear so that I can move on to one more question. Let me know fast, people. Perfect, a very simple and basic question this was, based on the vapor density measurement. Alright, let's move on then to one more question. This is one more question on the screen. Let's exactly see what the question says and what we are supposed to calculate. For the reaction 2 times HI in equilibrium with H2 plus I2 gas, the value of Kc is given to us as 4. If 2 moles of H2, 2 moles of I2, 2 moles of HI are present in a 1 liter container, then moles of I2 present at equilibrium will be. Let's exactly see how to solve this question. It's a very simpler one again. See guys, the reaction that's given to me is 2 times HI gas in equilibrium with H2 gas, right? And with this I'm writing I2 gas as well. This is the reaction which I have. Well, the equilibrium constant Kc value is given to us as 4. Perfect. At time t is equal to 0, initially, how many moles of HI do we have in the container? We have got 2 moles of HI in the container at time t is equal to 0. And at the same time, how many moles of H2 are there in the container at time t is equal to 0? There are some 2 moles, right, of H2 as well. And there are some 2 moles of I2 as well in the container at time t is equal to 0, right? Yes. This is something which is given to me as per the question. I'm given with some 2 moles of HI, 2 moles of H2 and 2 moles of I2 in the container at time t is equal to 0, right? Now let's assume at equilibrium, out of 2 moles of HI, there are some 2x moles which are being dissociated, right? So I'll be left with 2 minus 2x moles of this reactant at equilibrium, right? Now have a look. 2 moles gives 1 mole. So 1 mole gives 1 by 2 moles. So 2x moles are going to give me 1 by 2 multiplied by 2x. Value comes out to be x, right? So initially there were some 2 moles and some new x moles would have got generated, right? Similarly, we will see 2 moles are giving me 1 mole, right? 2 moles are giving me 1 mole. Perfect. So 1 mole gives me 1 by 2 moles. So from 2x, I'll be getting 1 by 2 multiplied by 2x. Value comes out to be x. Already there were some 2 moles in the container. There will be some x moles, x new moles of I2 which would have got generated at equilibrium, right? So people, these are the number of moles of your reactants and products which are there in the container at equilibrium, right? Well, the volume of the system is given to us as 1 liter. If I divide this term by 1, this term by 1, this term by 1, I will be getting the concentration of each reactant and product at equilibrium, right? Yes. So I'll be using the expression to calculate Kc. Kc expression is simply going to be concentration of H2 at equilibrium, which is 2 plus x, multiplied by concentration of I2 at equilibrium, which is again 2 plus x, so becomes 2 plus x square. This is 2 minus 2x, right? So it comes out to be 2 minus 2x raised power what? Raised power stoichiometric coefficient, that's 2. Perfect. Right? So just take this square common. It's going to be 2 plus x divided by 2 minus x. 2 plus x divided by 2 minus 2x raised to the power what? Raised to the power 2. Well, Kc value as per the question is given to me as 4, right? If I take root on both these sides, the value comes out to be 2 is equal to 2 plus x divided by 2 minus 2x. So from here, you will be getting the value of x, right? So it's going to be 4 minus 4x is equal to 2 plus x, right? So it's going to be 2 is equal to 5x, right? And from here, you'll be getting the value of x as 2 divided by 5. So value of x you got, 2 divided by 5. What was I supposed to calculate? I was supposed to calculate the moles of I2 at equilibrium. Moles of I2 at equilibrium is equal to 2 plus x. So 2 plus 2 divided by 5. Value comes out to be 10 plus 2, 12. 12 divided by 5, which comes out to be 2.4. So basically, there are some 2.4 moles of I2 which will be present in the container at equilibrium. So option C is the one which is going to be the correct answer of this question. Right, people? Perfect. Right? I'm sure it's clear to everyone. Let me directly move on to one more question then. I'm sure this sort of a question is clear to you now. This is a very basic question. This kind of question I've shown you in the beginning as well. I started the session with this question only. With this type of question I mean. Okay? So basically, what you need to do exactly, you need to calculate equilibrium constant for this particular reaction. Right? So what I'll be doing, I will be trying to make this reaction out of the given reactions. Now the point is, how do I make this reaction out of the given reactions? What I'll be simply doing, I will be first of all multiplying this reaction with 2. Or let me not multiply this reaction with 2. Let me just reverse this particular reaction. When I reverse this particular reaction, it becomes A gas plus half of Y gives C, right? On reversing the reaction, equilibrium constant is basically inversed, right? So initially it was 1 by 4, now it becomes 4. Now at the same time, I will be multiplying this reaction by 2. It becomes 2 times A plus Y gives 2 times C. On multiplying the reaction by a number, that number goes to the power of equilibrium constant. So what I simply did, I multiplied this reaction by 2. So that 2 will go to the power of equilibrium constant. So 4 2s are 16, right? 4 4s are, right? 16. 4 2s are 16, wow. Okay, so what I did, I got the equilibrium constant for this particular reaction. Now there is one more reaction that's given to us, that is 2 times A. 2 times A in equilibrium with what? 2 times A in equilibrium with B plus Y, right? And its equilibrium constant was given to us as 8. What I'll be doing, what I'll try to do, if I just add these two reactions, 2, that comes out to be 4 times A, Y got cancelled, in equilibrium with 2 times C plus B. So, am I getting the reaction for which I was supposed to calculate the equilibrium constant? I think I was supposed to calculate equilibrium constant for this reaction only, right? This is the same reaction. And how did I get this reaction? When I simply added these two, and on adding the reactions, equilibrium constants are to be multiplied. So 16 multiplied by 8, 16 multiplied by 8, 8 6 48, right? 8 1 8. So 128 is basically going to be the new equilibrium constant for this particular reaction which I was supposed to calculate. So option D is the one which is going to be correct answer of this question, right, people? I'm sure this is again clear to you, right? Again, a very simple and basic question. Just use the characteristics of equilibrium constant, that's all. Right? Okay, this is one more question. Let's try to see exactly what is something special in this question. See guys. 1 mole of N2 and 3 moles of H2 are placed in a 1 liter vessel. Find the concentration of NH3 at equilibrium if the equilibrium pressure is 1 atm and equilibrium constant at 400 Kelvin is 4 by 27. Now understand how this sort of a question I'll be solving. The reaction that's given to me is N2 and I'm making this N2 to react with H2. Absolutely it's going to lead to the formation of NH3. First thing, is it a balanced chemical equation? No way. Let's keep this 3 times, let's keep this 2 times, right? Now at time t is equal to 0, how many moles of N2 am I given with? I'm given with 1 mole of N2. And how many moles of H2 are there? There are some 3 moles of H2 as well. So this is going to be 0 at time t is equal to 0, right? Yes? Right? Perfect. Now guys understand. Let's assume at equilibrium, out of 1 mole of N2, there are some X moles of N2 which would have reacted with H2. So how many moles of N2 I'll be left with at the end? So there will be some 1 minus X moles of N2 left in the container at equilibrium, right? Now have a look. Since 1 mole reacts with 3 moles, so X moles are going to react with 3X moles. So out of 3 moles of H2, some 3X moles of H2 have got reacted. So I'll be left with 3 minus 3X moles of H2 at equilibrium, right? In the similar way, have a look. 1 mole gives 2 moles. So from x moles, you are going to get 2x moles. So these are basically the moles of NH3 present in the container at equilibrium, right? I got the moles of each reactant and product at equilibrium. Perfect. Well, the volume of the system is given to me as 1 liter. So divide this term by 1, this term by 1, this term by 1. I will be getting the concentration of each reactant and product at equilibrium, and then I'll simply use the expression for Kc. Kc expression is going to be equal. Concentration of NH3 at equilibrium raised power 2. So it's going to be 2x raised power 2, which comes out to be 4x square, divided by concentration of N2 at equilibrium, which is 1 minus x, multiplied by concentration of H2 at equilibrium, which is 3 minus 3x, raised by its stoichiometric coefficient, that's 3. Perfect. Well, Kc value as per the equation is given to me, I believe, it's 4 divided by 27. Is that? 4 divided by 27, right. So this 4 got cancelled first of all. So it's simply going to be 1 divided by 27 is equal to x square divided by. If I take 3 out from here, it is going to come out as 3 ka cube, that is 27. So it's going to be 27 multiplied by 1 minus x already was there. Now it's going to be 1 minus x ka cube. So this 27 would have got cancelled out. So I'll be getting one equation, and a very simple equation I'll be getting now. It's going to be x square divided by. It's going to be 1 minus x whole raised power 4. This value is equal to 1. Perfect. Now I can write the same thing like this. X divided by 1 minus x ka square whole raised power 2 is equal to 1. Right? Take square root on both the sides. It's going to be x divided by 1 plus x square minus 2x is equal to 1. Right? So from here you'll be getting one quadratic. Right? After solving this quadratic, can I get the value of x? Absolutely, I'll be getting the value of x. Right? So basically you'll be getting two values of x from here. Okay, you'll be getting two values of x from here, but you need to select the appropriate value. Perfect. After getting the value of x, you'll be just putting the value of x over here. You'll be putting the appropriate value of x over here into this part. This 2x is basically the concentration of NH3 at equilibrium. So 2 multiplied by x will be giving you the concentration of NH3 at equilibrium, and you can solve it afterwards, right? So from here, just solve this quadratic. Okay, get the value of x and put the appropriate value of x into this part. Right, you'll be getting the concentration of NH3 present in the container at equilibrium. I'm sure this is clear to everyone, right? Welcome, Vijay. Perfect, guys. Is it clear to everyone? I'm sure you got to know exactly how to approach, how to solve this sort of equation, right? So final answer will be coming out to be 0.762. Okay. All right. This is one more question. Let's exactly see what the question says. If the percentage dissociation is 40. Percentage dissociation means 40. What does that mean exactly? That means alpha value is equal to 0.4, right? If the percentage dissociation is 40 at 400 Kelvin and 1 atm pressure, calculate vapor density of the equilibrium mixture. I need to calculate vapor density of equilibrium mixture. That means I need to get the value of small d. Well, as per the vapor density measurement, this is again the case of dissociation, and alpha is going to be simply capital D minus small d divided by small d minus multiplied by n minus 1. It's a very simple and basic question, guys. Formula based question, right? See. Alpha value already I got to know as 0.4 is equal. Capital D is basically going to be the molar mass of reactant divided by 2, theoretical vapor density. What is the molar mass of this reactant? See, phosphorus is having 31, chlorine will be having 35.5 multiplied by 5. 35.5 multiplied by 5, right? This is the molar mass of reactant divided by 2 is going to give you the value of capital D. Can you let me know in the chats what is this capital D value coming out to be after solving? Fast. Can you let me know what is this capital D coming out to be after solving? It will be coming out to be 100 point something, I guess. Is that? Or no? Not 100 point something to be precise. Can you let me know exactly what is the final value of capital D which is coming out after solving this part? I'm waiting for your answers. Do it fast. So from here you'll be getting capital D, right? You'll be getting capital D. Minus small d is something which I need to calculate, I guess, right? So n minus 1, what is the value of n? See, from one particle you are exactly getting two particles, and the number of particles which we get from one particle of the reactant, that determines the value of n. So n value is 2, so 2 minus 1. What is the capital D, people? People are saying it's coming out to be 104.25. All right. So capital D value is coming out to be 104.25. So 0.4 is nothing. It is 104.25 minus small d divided by small d, right, multiplied by 1, right? So it becomes small d only. So you just got one equation which just contains one variable, and that variable is small d, and that small d is something which I call as the vapor density of the equilibrium mixture, which I was supposed to calculate. I'm sure you can solve it from here, and I'll show you the final answer. Final answer will come out to be 0.013. Perfect. I'm sure this is clear to everyone, right? Moving on to one more question, guys. This is one more question. Let's see exactly what the question says. Again, the basic question, and this question was asked in this year's JEE Mains examination, right? Very simple and basic one. So basically, we are doing the dissociation of PCl5. We are doing the dissociation of PCl5. And PCl5, when it undergoes dissociation, it leads to the formation of PCl3 gas plus Cl2 gas, right? At time t is equal to 0, initially I have taken some 1 mole of PCl5. So this is going to be 0, this is going to be 0. What is the percentage dissociation? 20%. What does that mean? That means at equilibrium, you'll find that 20% of the reactant would have got converted into product. If 20% of the reactant would have got converted into product, I will be left with some 1 minus 0.2 moles of PCl5 at equilibrium, right? So 1 mole gives 1 mole, from 0.2 you get 0.2, this is also going to be 0.2. So the value over here comes out to be 0.8, this is 0.2, this is 0.2, right? So what I got exactly? I got the moles of each reactants and products at equilibrium. Perfect. Can you just let me know what are going to be the total number of moles present in the container at equilibrium? It's going to be 0.8 plus 0.2 plus 0.2. So 1.2. 1.2 is basically the total number of moles present in the container at equilibrium. If I divide this term by 1.2, divide this term by 1.2, divide this term by 1 by 2. So can I say I got the mole fraction of each reactant and product at equilibrium, right? Since I got the mole fraction of each reactant and product at equilibrium, so multiply the mole fraction by the total pressure of the system at equilibrium, which is 1 atm, right? Multiply this term by 1, multiply this term by 1. So this is what I call as partial pressure of PCl5 at equilibrium, partial pressure of PCl3 at equilibrium, partial pressure of Cl2 at equilibrium. Since you got the partial pressures of each reactants and products at equilibrium, so what I'll be doing exactly, I will be writing the expression for what? I'll be writing the expression for Kp. That's going to be partial pressure of PCl3 at equilibrium, that means this term, multiplied by partial pressure of Cl2 at equilibrium, that means this term, divided by partial pressure of PCl5 at equilibrium, that means this term. So finally, you'll be getting the Kp value exactly. And let me show you exactly what the value comes out to be after solving. The value comes out to be 1 divided by 24. People, just let me know in the chats if it is clear to everyone so that I can move on to one more pattern of the questions. A very simple and basic question this was. I'm sure you would have solved it properly, okay? Look at this question, guys. What the question says exactly. Let's read the question first. In a reaction A plus B in equilibrium with 2C plus D, all right, initial concentration of B was 1.5 times that of A, okay, but at equilibrium the concentration of A and B became equal. The equilibrium constant for the reaction is, see, it's again the simple question. The reaction that's given to me is A plus 2B in equilibrium with what? In equilibrium with 2 times C plus D. This is the reaction which is given to me. And as per the equation, there is one parameter given. Initial concentration of B is 1.5 times A. Let's assume the initial concentration of A is 1. So B is going to be 1.5 molar, right? Because initial concentration of B is 1.5 times A. Perfect. I'm assuming the initial concentration of A is 1 molar. So this is definitely going to be 1.5 molar. So this is going to be 0. This is going to be 0. Perfect. Now let's assume at equilibrium. First thing, I'm going to treat these concentrations in the similar way as I used to treat the moles, right? So this is going to be 1 minus X. This 1 minus X is the concentration of A left in the container at equilibrium. Since 1 mole reacts with 2 moles, X moles are going to react with 2X moles. So I'll be left with 1 minus 2X, right? This is going to be the concentration of B left in the container at equilibrium. Now 1 mole gives 2 moles, from X moles you are getting 2X, right? And this is going to be X. Perfect. So you got the concentration of each reactant and product at equilibrium. Perfect. What do I need to calculate? Okay, there is one more term that's given to me. At equilibrium, the concentration of A and B became equal. So at equilibrium, the concentration of A and concentration of B are equal. So I must say, at equilibrium, 1 minus X is equal to 1.5 minus 2X, right? So the value comes out to be, this will go on that side, right? So it's going to be 0.5. This will come here. So X value is coming out to be 0.5. Perfect. Since you got the value of X, if you got the value of X, 1 minus 0.5 comes out to be 0.5. This is the concentration of A at equilibrium. 1.5 minus 2X. 1.5 minus 2X. Is it basically 1 minus X, and 1 minus X is nothing. That will come out to be 0.5 only. So this is 0.5. 2X value. X is 0.5, so 2X is going to be 1, right? And X value, that is 0.5. Since you got the concentration of each reactant and product at equilibrium, so what you'll be doing now, you'll be simply writing the expression for Kc. Isn't it going to be concentration of C at equilibrium, that's 1, raised to the power 2, right? Multiplied by concentration of B at equilibrium, that is 0.5, raised power its stoichiometric coefficient, that's 1, divided by concentration of A at equilibrium, that's 0.5, multiplied by concentration of B at equilibrium, which is 0.5, raised power its stoichiometric coefficient 2, right? Just solve it, get the value of Kc. That's something which I was supposed to calculate, right? A very simple and basic question this was, and finally after solving, you'll be getting the value of Kc exactly as 4. Perfect, people. Is it clear to everyone? Is it clear to everyone? Let me know fast. Yeah? Perfect, guys. Moving on to one more question, let's have a look on this question. And even this question was asked in this year's 2021 JEE Mains, right? And a very simple and basic question this was. At 1990 Kelvin and 1 atm pressure, there are equal number of Cl2 molecules and chlorine atoms in the reaction mixture. So basically, you've got a reaction mixture containing Cl2 and Cl present in the container at equilibrium, right? Okay, perfect. Now guys, as per the equation, at equilibrium, the number of molecules of Cl2 are equal to the number of atoms of Cl. So what does that mean? Can I say at equilibrium, the moles of Cl2 will be same as that of moles of Cl? As simple as that. So whatever are going to be the moles of Cl2 at equilibrium, same are going to be the moles of Cl at equilibrium. Since if you know the moles of each, let's say this is X, so you can calculate mole fraction, right? Total moles present in the container at equilibrium is going to be X plus X2X. So X divided by 2X, the value comes out to be 1 by 2. So you got the mole fraction of each. Multiply their respective mole fractions by the total pressure of the system, which is 1 atm. So you'll be getting the partial pressures. Once you get the partial pressures, you can write the expression for Kp. So I'm directly showing you the solution of this. Have a look exactly. This is the reaction exactly. Your molecular Cl2 is getting converted into your atomic chlorine, right? And at equilibrium, whatever molecules of Cl2 were there in the container, same are going to be the number of atoms of chlorine at equilibrium present in the same container. As simple as that, right? Let's assume there are some X molecules of, or let's assume there are some X moles of Cl2 in the container at equilibrium, right? So this is also going to be X plus X2X. So at equilibrium, total moles are going to be 2X, divide total moles to X. The value comes out to be 1 by 2. Over here, the value comes out to be 1 by 2. You got the mole fraction of each reactant and product. So multiply the mole fractions by the total pressure of the system at equilibrium. So this is what I call as partial pressure of Cl2 at equilibrium. This is the partial pressure of Cl at equilibrium. Since you got the partial pressure of each, then write the expression of Kp and kill the equation. That's all. Perfect. Very simple and basic question this is, right? Okay, one more question we have. See what the question says. The equilibrium constant Kp for the reaction. The reaction that's given to me is nothing, that is PCl5 in equilibrium with PCl3 plus Cl2, right? The equilibrium constant Kp for this reaction. So Kp for this reaction is given to me as 1.6 at 200 degrees centigrade. The pressure at which PCl5 will be 50% dissociated at 200 degrees centigrade. People, even this is the simpler question. I've shown you this sort of equation a few minutes back only, so let me not do it, right? It's a very simple one. The same procedure you are going to follow, right? You'll be starting with the initial moles of PCl5 as 1, 0, 0. When 50% of the reactant has got dissociated, when 50% of PCl5 would have got converted into the products. So at that point of time, I'll be left with 1 minus 0.5, right? So 0.5 moles of PCl5 will be still left in the container at equilibrium. 1 mole gives 1 mole, from 0.5 you get 0.5, this is 0.5. You got the moles of each reactant and product at equilibrium. So calculate the total moles, sum of all these. Divide all these moles by the total moles of the system at equilibrium, you'll be getting the mole fractions. Multiply that by total pressure of the system at equilibrium, which is P. Right? So this is basically the partial pressure of PCl5 at equilibrium, and similarly partial pressure of the other substances. Then use the Kp expression, get the value of P. Perfect. It's a very simpler and common question again. This sort of equation I've showed you a few minutes back only. That's why I'm not showing it now. Okay. And people, if you have not enrolled into the Vedantu JEE 2022 crash course batch yet, which has started on the actual Vedantu platform, do it as soon as possible, right? In this crash course, which has started on the actual Vedantu platform, we will be covering your whole syllabus in your physics, chemistry, as well as mathematics, right? Apart from that, no need to worry about the test series, no need to worry about the assignments, no need to worry about the study material. Every single thing will be provided to you from our side, right? And this course is completely affordable just for 9K if you'll be using this coupon code WBPRO, right? So let me show you exactly how to get enrolled in this one, in this crash course program. This is the video which you guys are currently watching, right? Just drag the video a little down, click on show more. After clicking on show more, you'll be getting a lot of links over here. Avail all exciting Vedantu crash courses by clicking on this link. JEE crash course, click on it, right? After clicking on it, you just need to drag it a little down, okay? Just click on buy now and use this coupon code WBPRO or WBJCC and put your number, email ID on which you'll be getting OTP and everything, and eventually you'll be getting enrolled into the crash course batch which just started on the actual Vedantu platform, right? Which is basically a result oriented batch, right? Every year in Vedantu platform. So do get enrolled as soon as possible, okay? So people, the session has ended, right? I'm sure you would have got a lot of new things, you would have understood a lot of new things, and your chemical equilibrium chapter would have got revised properly, right? Perfect. So with this, I'm going to take a leave here. I'll see you guys day after tomorrow at the same time, right? With the JEE mock test number 11. Do not miss that at all. See you on Monday sharp at 9:30. Till then, you take care. Bye-bye. God bless you all and love you all. Take care, guys. Bye. Take care, people. Take care. Bye-bye.